Hello everyone, my name is K. Naveen Kumar and my roll number is 21955A2106 and I am from Aeronautical Engineering Section IARE College. And and the tech talk topic on DES data structures, and my topic is application of splay trees to the data compression. And coming to first of all, I want to explain about data structure. And the data structure, the subject which is it is it is used to store the data. Uh, and coming to this topic, the splay prefix algorithm, it is one of the simplest and fastest adaptive data compression algorithms based upon the use of prefix code. And data structures are used in the splay prefix algorithm can also be applied to the algorithmic data compression. Application of this algorithm to the encryption and image processing and suggestions. And I want to tell that Splatrix, it is also known as it is a type of data structure. It is to store the data. Data compression algorithms can improve the efficiency with which data is stored or transmitted by reducing the amount of redundant data. A compression algorithm takes place a source text as input and produces a corresponding compressed text, while an expansion algorithm takes the compressed text as input and produces the original source text as output. And the most compression algorithms view the source text as a consisting sequence of letters selected from an alphabet. Platters usually consider forms of lexicography graphically ordered binary search trees, but the trees used in data compression need not to have static order. The removal of ordering constant allows the basic playing operation and considerably simplified. And here the split trees, it is a type of data structure and it does not require any static header to remove or to remove the data from that. So this is the one of the features in the split trees, and it does not require any order to remove the data. Yes. And coming to this slide, the resulting algorithms are extremely fast and compact when applied to a human Hoffman codes. Playing load lead to a locally adaptive compression algorithm that is remarkably simple as well as fast, although it does not achieve optimal compression. When applied to the arithmetic course, the resultant is near optimal in compression and asymptotically optimal in time. Here, here when we comparing this arithmetic codes, the resultant is optimal, and this is locally adaptive compression algorithm. This is remarkably simple and very fast. So it is applicable for the Huffman codes and for this optimal times. And prefix code which is used in the state trees to store the data, and this is the one of the most widely used studied data compression algorithms are probably those based upon Huffman codes. Mm. And in a Huffman code, each source letter is represented in the compressed text by the variable length code, and the common source letters are represented by the short codes, while uncommon ones are represented by the long codes. And the codes used in the compressed text must obey the prefix property. mm, that is, code code used in the compressed text may not be is a prefix of any another code. Here I want to tell what is a prefix. Prefix that means uh, the the what I say the operator should be before the operand, then it is called prefix. This is the prefix code should be property must be remembered to write this code, and this is commonly used in human code, and it is represented by a compressed variable length code, source code. Arithmetic code. It is the one of the code which is used to store the data in the space trees. So coming to this, the compressed text resulting from this arithmetic data compression is viewed as a binary fraction, and each letter in the alphabet is associated with the different subrange of open interval, 0 and 1. The source text can be viewed. The source text can be viewed as textual representation of fraction using the number of systems, where each letter in the alphabet is used as a digit, but the range of values associated with each letter as width depending upon the uh, frequency of the letter. And this is the code which is used based on, these are the terms involved in that to store the data. If you see, this is viewed as a binary fraction, and the source text is viewed by the textual representation of fraction number. And coming to this, alphabet used as a digits, and but range values are associated with each letter depending upon the frequency of the letter. And this is the conditions followed, rows. This is a followed arithmetic code. And this is to see, this is the diagram which is representing this A, B, C, D and 0, 0, 1, 1, 1. And if you want to store the data, if you enter this, A is equals to 0, 0, 0, and if you want B is 0, 0, 1, and if you want to go for C, and it is 0, 1, and if you go for D, and it is 1. And this is jag rotation, and in this practice we have two types of rotation. One is zig rotation, and another one is jag rotation. It's a single left rotation is called jag rotation. Right rotation is called zig rotation. And if you see this variables like 2, 3, 5, 4, 6, if you see this 5, 6, 3, 2, 4, so this is the rotation. If from here to here it is converted by the jag rotation code. Some of the real-time applications of data compressions, it is used to implement the caches. It has the ability of not to store any data, which results in minimization of memory. These are some of the special features, and which will indicate that memory requirements it will store. This as one special feature we should consider, and it can also be used for the data compression example for dynamic human coding. Applications of data compression via split trees. Suppose we want to compress text over the same element sigma. Prepare binary tree containing of items sigma x leaves, and to encode the symbol x, transfer the path from row to x emitting 0 when you go for the left, I when you go for the right, and display symbol is x used for the new tree encode the next symbol. And this is the process, how should to apply how to should apply data compression through the state trees. These are the steps involved, and I want to tell finally state trees about plate trees. In the balanced tree scheme, expect rules are followed to ensure a balance. In split trees there are no such rules. So such insert and delete operations are like in binary search trees, except at the end of each operation, A special step called splaying is done. Splaying ensures that all operations like O of login optimize time and this first preview of BST hours. Here the splay trees are the ones with the data structure which is used which does not use the insert and delete operations like binary search. And these are done only by an splaying operation. Splaying inserts the operations like zero off, and this will indicate the time. And the main aim and motto of this application of this data compression to this displaying trees is to compress the data in how in a existed space, and it is to reduce the space complexity and space complexity to understand the data in clearly and neatly. And finally, thank you for listening my PT or TikTok.